Today I want to talk to you about another independent researcher named Jeff Yee. Now, Jeff Yee has a YouTube channel called The Energy Wave Theory. Now, I know I've mentioned him from time to time in other videos and in my comment section, but this time I wanted to dedicate a video to him and his research because it's pertinent to a lot of the work that I do. Now, I became aware of Jeff when he was interviewed by my good friend David Hilster from the John Chappell Natural Philosophy Society. Now, David has his own YouTube channel called Dissident Science, and he interviews people and he discusses his own research, his own independent research, and on this channel. So this is another channel that you may want to check out. So I became aware of Jeff's work after I saw this interview, and so I decided to read his book. Basically, the interview was about the release of his second edition of his book. So the book here, you can find on Amazon. It's called Particles of the Universe 2 Disrupted. Now, there is a Particles of the Universe 1, the original book that he wrote, which is also on Amazon. And I downloaded both books, but I really only read this book. And so after reading this book, actually, I was on vacation in the Bahamas and the weather was really bad and I had lots of time to read. And so that is when I read this book and I had lots of time to give it a thorough go over. And so it's very well written. It's an easy read. Generally, it's an easy read. I enjoyed reading it as well as finding out more about his theory. And so his theory, which is a wave model of particles, is founded in the work of Milo, which you can look up and find out more about this model. So basically, this model is let me just read the abstract a little bit, just to give you a foundation. Okay, so the structure of the electron is investigated and found closely entwined with the origin of natural laws. The natural laws had been measured for hundreds of years, but no one knew how nature creates them. Okay, so then he goes on to talk about, Richard Feynman and the conservation of energy. Nature has a hidden accountant who keeps honest books of energy input and output, but we don't know how she does it. So the origins have been proposed earlier by Clifford and Schrödinger, who pointed out that only a wave structure of matter can explain these natural laws. Okay, and further he says Einstein realized that matter was spherical and spatially extended, and thus the electron was not a point particle, but rather a structure of space. So, so this spherical structure is the foundation for Jeff's theory, and so this is his starting point. Okay, so again, the spherical geometry, the spherical wave has an ingoing wave and an outgoing wave. And so it's got a standing wave and a traveling wave. So the standing wave is the spherical standing wave is the particle, and the outgoing wave becomes a traveling wave. So the incoming wave contributes to the standing wave, and the outgoing wave would be the wave leaving at a certain boundary condition. And Jeff explains all this in his video, so I highly recommend that you watch his video series and or read his book. Okay, really I'm just giving you an introduction to his work. I'm not going to explain his work in any detail. So here is an image from his book. And this shows the standing wave. There's a standing wave. And he's got a concept called wave center. So there's a wave center. There's a standing wave. And so the particle part is the standing wave, and it's got a radius. It's got a particular radius. And there is the boundary condition right here. This is the boundary condition of the standing wave. And outside of the standing wave are the traveling waves. Okay, so the traveling waves go into the wave center and come out of the wave center and create the standing wave that we perceive as the particle. And this is just a depiction, a schematic of what he's talking about in his theory. Okay, so here is another figure from his book, and this has to do with the electron. So basically he's saying the electron is a spherical wave, a spherical standing wave with a certain number of wave centers. And so he's saying the number of wave centers is proportional to the wavelengths, and more specifically the number of shells that hold the energy of the particle until the standing waves decrease in amplitude and transition to traveling waves at the particle's radius. So the particle's radius is the transition from the standing wave condition to the traveling wave condition. And so this image on the right, so he noticed that there was an experiment that was done by scientists in Sweden where they claimed to have filmed a moving electron for the first time. And what he noticed, what Jeff noticed, was that the number of spherical contours in this image, it looks like it's about 10, and in his model the number of spherical shells is 10. And so that, was a little bit confirmation of his model. Okay, and then, he goes on to talk about the different kinds of waves, and I think this is really important. It's a good review. You have transverse waves, where the particle movement is orthogonal to the direction of travel of the wave. And you have longitudinal waves, where the direction of the wave, the direction of the particle movement is in the same direction as the direction of the motion of the wave. And so here he's outlining the 4 kinds of waves. Okay, you've got longitudinal and transverse waves, and you have standing and traveling waves. And so these are just the wave types. For waves that are in motion, you have standing and traveling waves. And the 2 sort of modalities, or the 2 kinds of waves, are the longitudinal and the transverse, in the most simplistic form. Okay, so in Jeff's model, he's got 2, I'm going to call them incommensurate principles. In my opinion, these are 2 incommensurate principles. You've got the ether granules, so these are the granules that make up the ether itself, and then you've got the wave centers. And so I'm just going to read here what he says, just for clarification. So in his model, the ether is the fabric of the universe, and it consists of 2 basic things that need to be defined. The terms that will be given to these items, these things, are credited to 2 pioneers of wave theory, Gabriel Lafreniere, I believe I'm saying that right, who was referenced in the section on the ether and Michelson-Morley experiment, and Dr. Milo Wolf, who calculated the wave properties of the electron. So in his book he says the granule is the term given to the smallest component of the universe that makes up the ether. Like the water molecule that pushes the next water molecule in a pool to create a wave, or the air molecule that pushes the next air molecule to create a sound wave, this is the unit that is moving and passing energy from one granule to the next granule. While we cannot see or verify this small granule, we can infer it from the equations and from the equations that he shows in his book. Okay, so there's another section from his book, continues on. While a granule transfers wave momentum in the direction of motion, just like the waves in the pool, a wave center does the exact opposite, which is why I say that granules and wave centers are incommensurate principles. They're doing completely different things. Okay, so the wave center reflects the wave backward in the direction of motion. It is similar to the wall that was constructed at the edge of the pool to protect the man. The wave reflects backwards, combining with another incoming wave to produce a standing wave. So, or using a guitar string analogy, granules would be the material of the string itself, while the wave centers would be the material at the fixed ends of the strings. Okay, these two things, granules and wave centers, are the only components of the universe. So this is super, super simple. I like this because he has two incommensurate principles which make up the whole of the universe. So all the properties of matter and the forces that act upon matter can be described with just these two components and a set of basic laws by which they operate. So this is this is the foundation of his theory. And what he does is he shows how all of the constants of nature can be derived using this model. Okay, so Particles of the Universe Disrupted, you can get a Kindle version on Amazon for $2.29. Practically nothing. So I highly recommend this book. It's a good starting point for his theory, but if you don't like reading books, then his video series is the next best thing. So I just want to warn you, if you do buy his book, you're going to find equations that look like this. You're going to find equations that look really complicated, and to be totally honest, when I saw these equations at first, it scared me a little because I'm looking for a very simple theory of the universe, and this looks kind of complicated to me. But it turns out this is not as complicated as it looks, because most of the parameters in these equations are really just constants. And so what he's done is he's taken basically the constants of nature and like ripped them apart and exposed them for what they are, and then he puts them back together in his future work, and simplifies things quite a bit. So I just want to let you know that I took some of these equations and I crunched the numbers, just to make sure they were right, and all of the equations that I tested did in fact produce the values that he was claiming they produced. And so I think I crunched enough of them to convince myself that at least he's not making a mistake. Okay, so here's an example of the magnetic constant, and you can see here is the formula that is commonly used to calculate the magnetic constant. It is 1 over the permittivity times the speed of light squared. And so here is his equation for the magnetic constant, and you can see it looks really complicated. But only because he was breaking the constant of nature apart and fitting it into his wave model, and then studying that. And so I have no problem with this now that I understand what it is, and that it does in fact give you the correct value that we need for the magnetic constant, for the permeability of free space. Okay, so after I read the book, I came back from my vacation and I contacted Jeff and I said, really good job. I really liked your book. I like how how he connected his constants with the constants of nature, and and that he addressed a lot of the equations, the common equations in physics, using his model. And so what he said to me was, he said, the only equations he hasn't been able to fit his model to were Maxwell's equations. Okay, so Maxwell's equations are a little bit of a different beast. And so he was trying to figure out how to do this. And so at the time, I was studying another independent researcher, Robert Distinti. And I was really taken with these equations that Robert came up with, which were basically force equations. These were force equations that can be related to magnetism. So the Maxwell's equations have the magnetic field abstractions. So Robert Distinti is not a big fan of the B field and E field abstractions. He prefers force equations, and I prefer force equations. And so I went back to Jeff and I said, well, what if you don't need to map your equations to Maxwell's equations? What if instead you map your equations to Robert Distinti's force equations? And that was a game changer for him, I believe. He had a ding, ding, ding revelation moment. Once he had a look and studied these equations, he was able to map his equations to Robert Distinti's force equations. And so I'm not going to get into the details of this. This is another story, maybe for another video. But this gave Jeff the confidence to move forward with his theory. And not only that, but he gave me credit for connecting him to Robert Distinti and to these force equations. And so then we began a more detailed collaboration. Okay, so I'm just going to quickly go through these force equations, not in any great detail. Like I said, it could be another video, but these equations are basically cover everything. What Robert did was he quantified all the ways that charges can move relative to each other, and wrote an equation for each of those situations. So the first one here is really just Coulomb's law. The last one here is really just Newton's second law. Okay, F equals ma. This is really force equals mass times acceleration in disguise. Okay, and there are two forms of this equation. One is a force equation and one is a momentum equation, but they're basically talking about the same thing. This is a charge in acceleration. Okay, and then he came up with three equations that have to do with magnetism. And so there is a force equation already in magnetism, F equals QV cross B, but again you have the B field abstraction that Robert is trying to get away from. So he needed three equations to mimic this force equation. Okay, so long story short, Jeff Yee did not need to deal with Maxwell's equations. He went directly to Robert's equations and was able to map his equations to those equations, and had I'm going to say a bit of a breakthrough in his theory, and we moved forward from that point. Okay, so what came out of that was a paper which he named me on because he gave me credit for showing him the work of Robert Distinti. And so we wrote this paper, which is on ResearchGate, and which he presented to the John Chappell Natural Philosophy Society that same year. And so this paper, you can read it, and this is, the first iteration of connecting his work to Robert Distinti's work. And I just have to say that I'm really grateful and honored that Jeff has agreed to name me on his papers. It gives me incentive to work hard to try to, to help him out and to, find mistakes in his papers, read his papers, study his papers, and maybe give him other ideas and to move forward with his theory. So the next paper we wrote was it's called Particles of the Universe Meets Electric Universe. So this is connecting his theory to the electric universe, and I'll just read the abstract here just to give you an idea of what this is. In this paper, the electric nature of the universe is revealed by applying the language of electronics to the energy and forces acting upon subatomic particles. Okay, and I'll read the introduction too because it's short. So, a quest for grand unification in physics community is the holy grail quest, in that whomever solves this big problem will likely receive a Nobel Prize. Now, we're not under any illusion that we're getting any Nobel Prize, but it's still kind of fun to think about. This is a big problem that needs to be solved. And everyone is looking for the grand unified theory of the universe. So, it is generally understood that this unification will involve the unification of relativity and quantum mechanics. That said, the unification with the domain of electronics does not seem to be on anyone's radar, even though this would also be a huge breakthrough. If all the forces in the universe, including gravity, can be explained in terms of an electric universe, then the path to unifying relativity and quantum mechanics may be greatly simplified. Okay, I wrote this. I like this idea of taking a different path to unification because I think that's the right thing to do. Okay, so then there's a few more papers that we've written together. The geometry of space-time and the unification of electromagnetic, gravitational, and strong forces. Now, so I'm not going to get into this one. Well, maybe I'll read the abstract just to give you an idea what this one's about. So in this paper, a space-time structure consisting of a body-centered cubic lattice. So this is where the lattice comes in. So now maybe you might understand the last two videos that I made where I took a lattice and I'm vibrating the lattice and creating some graphics, because the idea here is to be able to simulate now. So the next step for Jeff's work is to be able to simulate his model. And so it's in this one where he introduces the BCC, the body-centered cubic lattice, to map out his theory, to map out his model, and for us to be able to simulate it. So the body-centered cubic lattice is modeled classically as a spring mass system. And so that's why I'm using a spring mass system. I'm playing around with a spring mass system to see if this can lead us to a simulation of his model. Okay, so the spring mass system, where the components of each unit cell in the lattice is based on the fundamental units discovered by Max Planck. These are Planck's natural units that I've talked about before. And the common forces that govern the motion of particles in space-time is defined and unified by geometric shapes as the space-time lattice oscillates. So that's why I'm trying to create an oscillating BCC lattice to try and mimic Jeff Yee's space-time model. And here is just a picture of a spring mass system. And this is just one unit cell. There's the center of the cell and the outer outer dimensionality of the unit cell. So the dimensionality uses Planck length. So Planck length is the radius of the granules. Planck mass is the center of mass, is the mass of a unit cell. Planck charge, Jeff deals with Planck charge and with charge in general a little different than the standard model. He models Planck charge as wave amplitude and gives it the units of the meter. And so this is a huge divergence from standard unit analysis. And so he refers to this as modified unit analysis, using the term that I created, because literally we are modifying standard unit analysis to model this system. Okay, and then the Coulomb force is the spring itself, is the spring constant in his model. And so this is basically, these are the parameters we're going to use, hopefully, to be able to model his space-time lattice. And so that leads us to this final paper, which we just released, The Physics of Subatomic Particles and Their Behaviors Modeled with Classical Laws. So this gives more details as to the space-time lattice that we're trying to model. And of course, I'm going to be honest with you, I wrote very little of this paper. I maybe changed one word. This paper was perfect the first time I saw it, and aside from a couple of little details. And so really now my contribution is going to be to try to simulate his space-time model, his grand unified wave energy model of the universe. And so that's about it. I'm going to leave it at that, and I'm going to leave links to everything I talked about in this video in the description. And I hope, you know, I a little bit feel like I've been holding out on you guys. I haven't talked about this much because, number one, I wanted to wait till I had, you know, a large number of subscribers to make a big impact. And I want to, you know, be further along with, you know, trying to model this before you know, getting into it in too much detail. So finally, I'm just going to run a little simulation. This is another simulation of what I'm working on. This is just a slab of space that I'm trying to model with spring masses. And so the inner part is the lattice, and I'm really just doing a bunch of perturbations. This is like this, you know, you can think of it as the space-time foam that they talk about in standard physics. It's basically like a trampoline. I took the outer red part here is basically not allowed to move, and the inner part is allowed to move, and I'm just perturbing the lattice to get space-time vibrations. But this is not even close to what we want to do. This is just the starting point. There's still a lot of work to do, but I'm having fun playing with this and seeing what this toolkit that I'm working with, which is called the Titan. It's a spring mass simulator that I found, and this is what I'm using to generate these simulations. And so I'm going to leave it at that. This is almost 30-minute long video. I thought it would be shorter, but it's not. So I hope you enjoy it, and I've got a few other videos in mind that I want to do this weekend. I've got some time to kill, so hopefully I can pump out a couple more videos as well. So I hope you're having a good day, and we'll talk to you soon.